Hey everyone, I am joined by David Kanter today. He's joined us before, and from Real World Tech, also mlperf.org, has some contributions there. And today we're talking about Intel's new announcements. So things like the 3D approach to CPU design, really interesting stuff. We're gonna go pretty technical on this. Also, we just got done at the event and we have no good set option. So we're in a hotel, for which I apologize. But you can listen to the video, it's great content, and we're going to talk about some technical details today. Before that, this video is brought to you by Thermaltake's Core P3 case. The Core P3 is one of the most unique cases on the market. It can serve as an open-air standing chassis, a test bench in vertical or horizontal orientation, or as a wall-mounted showcase PC. The Core P3 now comes with a 5mm thick tempered glass panel for its side, but keeps the front, top, and back open for air. The Core P3's versatility as a display piece, test bench, or standard desktop is reinforced by its price of roughly $110 on Amazon. You can learn more at the link in the description below. Our main topic today, we're going to be talking about this new Intel discussion. So we were both out here in the Bay Area for talking about Intel's upcoming Sunny Cove was, I guess, the main one. And then just the architecture in general. They had IGP stuff, they had FPGA, they had a bit of everything today.
Yeah, and I mean, I think the other thing is that it was, for the last 2 years, it's been somewhat difficult to get technical information out of Intel about different things, and part of it is it's sort of on the big core side been Skylake for a long time, and some of the Atom cores they don't really publish a lot of details about.
14 nanometer for a long time,
right? And
which is changing.
Yeah, and so. I think that the point of today was really to talk about, okay, here's what we have coming, here's what we're doing, and here's how we think about, plugging in technologies and making them work together to deliver awesome products over the next few years.
So then what, I don't know, there's a lot of stuff. We'll have some online already, and there'll be news reports with all the basics, but one of the bigger things here is, I guess, the 3D approach to design. So I mean, it's I think I have some photos of it, but they had diagrams showing like 3D stacked components, right? And this is not necessarily a new idea, but it's new to see it implemented by Intel, as far as I'm aware.
Yeah, well, and I think it's also so to back up, like let's just start out with like what's going on with 3D and packaging and 2.5D, because there's tons of terms out there, and frankly, it can be a little confusing.
Yes, what is 3D even a valid term, or is it a marketing term? Is that a technical, correct term?
Yeah. So actually, conveniently, it is. And that's also one of those ones that actually sounds good from a marketing standpoint.
So it's not like 3D Crest White.
Yeah, no, definitely not. No, and I don't think there's any blue sparkles with this one either, so added bonus.
Yeah.
No, so if you look at traditional chips as we built them, you get a single chip, and if you're lucky, everything's integrated on there, or almost everything. And so what we saw with Vega and with the high-end Volta V100 and the P100 before it is that you can do what's called a 2.5D stack, where you have chips together in the same plane, so it's not truly 3D, but then there's a backing interposer.
Right.
And so that allows you to connect them up over metal wires that go through silicon as opposed to through the package.
Does Fiji fall into this as well, or the Fury X?
Yeah, so I think that was the first to use HBM, high bandwidth memory. And so that was one of the first examples of commercial usage.
2.5D, would you call that?
Yeah, 2.5D, right? Because it's sort of going vertical, but not quite. And then, so Intel came along, and they have a customized version of that called EMIB, the Embedded Multi-Die Interconnect Bridge. And that's a little bit different. It's sort of more two-dimensional, but with a lot of the benefits of 2.5D at a lower price point. And that's actually used in the Stratix 10 FPGAs currently, and may be used in other contexts as well, sort of in future products. And it is also used actually in the can't remember the name of it, but
at the event today.
No. The Intel CPU with the Radeon Vega graphics.
Hades Canyon.
Yes, Hades Canyon. Yeah, so that actually uses EMIB, is my understanding. So anyway, so the next step beyond that is, rather than taking our dies side by side and then attaching them through some sort of silicon underneath, is to have them one on top of another and to connect them up vertically. And so I actually thought that they did a great job talking through some of the challenges of that, but also some of the opportunities. So, I think you were the one who actually asked the question. We were in a round table together of, okay, well, if we're going to take a bunch of pieces of silicon,
right,
how do you cool them?
Yeah, so because you have, as they show on the photo, is it correct to call it logic dies? Is that what they are? Or what?
Yeah,
logic units,
I mean, they can be different dies.
Right, sure.
But
either way, the point is that you have some on the bottom, some on the top. You got something in the middle if it's three-dimensionally stacked.
Well, if you have three of them.
Or if you have three of them, right. And if you have three of them. And so you end up with one in the middle that has no direct connection to a surface on top or a surface on bottom.
Right.
So how do you cool it?
Right.
And we did talk with Jim Keller about this a little bit.
Yeah. And so realistically, in most packaging solutions, only one of those die is going to be directly connected with your heatsink. So that guy will cool really well.
The other one, is the bottom layer an interposer? Is that the most immediate layer?
Well, so in 2.5D, it's interposer and then active chips on top. So there's only one surface emitting heat for all intents and purposes.
Right.
And so the cooling for that is pretty straightforward. But where you get to 3D, where maybe you have several different layers of logic, now all of those are active, so they're switching, so they're all burning power,
right,
and emitting heat. And so there's no real interposer there necessarily.
Okay.
I mean, you might have it, but yeah, so then the challenge is, well, okay, which die do you want to be touching the heatsink? And then how does everyone else dissipate their power? And what's the order that you do it in? So, for example, memory, DRAM, when you heat it up, the leakage gets worse, so the refresh time needs to be more frequent, right? So that's going to hurt your performance, and it's bad news all around. So, you don't really want to have the DRAM necessarily sitting right on top of really hot stuff, like, say, your floating point unit.
Right.
And so, when we got into the discussion...
And he brought up registers as well, I think. Yeah,
register files, or backing up, when you look at a CPU core, there's some parts that are going to be really hot, like register files, floating point units, anything that's switching a ton on a really regular basis, like every clock. When you look at a thermal image, those are the red spots. I remember the Pentium 4, the red spots was those double pumped ALUs that were running at like 10 gigahertz.
Right.
And it's like, oh yeah, that burns a lot of power.
Yeah.
Right.
Yeah.
Don't put that near anything sensitive. So, and then you have like your cache arrays, which are frequently inactive because you're only going to be accessing one line at a time, maybe two or three. That's going to be much cooler overall. And so, the answer that I heard was, there's no magic bullet for cooling. There's just careful design and planning, and place things accordingly.
Right.
So
don't put very hot things next to things that are very thermally sensitive.
Yeah.
Yeah. And
then the other aspect is, how do you get the power in? Right. Because if you take a look at Ice Lake Server or any of these really big high-powered chips, they've got thousands of pins, of which many are used to drive power in, and ground pins. And so that's fine, but if we're going to go stacking things, not all of those have pins that are directly connected to the outside world.
Right.
And so if you're, imagine you're like a 10 high stack. Well, the guy who has to go through 9 others has a worse power delivery network and a worse ground plane than everyone else. And so how do you cope with that? And again, the answer is design. Although I would say in terms of power delivery, Intel's voltage regulators, the fully integrated voltage regulator that they had in Haswell and in Broadwell, and in their server chip still could be very useful. You could imagine having a dedicated voltage regulator on each layer.
And they were not able to confirm its existence in the upcoming products.
Yeah, they didn't seem too keen on talking about it.
Yeah, we did ask, and I believe the answer was Raja looked over his shoulder at PR and
yeah. I mean, I suspect it'll be back, but we'll see. Read and find out, as they say.
Yes.
So I thought those were some of the issues. And then the other thing that Raja mentioned was the known good die problem, which is that we don't want to connect up multiple dies into, say, $1,000 chip, and then only later find out that one of them was bad.
Right. So how do you deal with that?
Yeah,
pre-testing or?
Yeah, well, so you can do testing pre-packaging, but it's added cost, added complexity.
That sounds very logistically expensive.
Yeah, and you can't test everything. Obviously, if you only put it into a package afterwards, you can't test the package.
Yeah.
And so if you break things in the packaging process, well, you're stuck.
Yeah.
Unless you can map those out. So, I think those were some of the key areas they identified, but to me it's really exciting because one of the things they didn't get into a lot, in part because it's not a manufacturing event, is what are the things that it unlocks?
Right.
And so I think a lot of it is just giving designers a lot more flexibility.
Yeah, and they mentioned that this opens a lot of doors that they didn't really explore for today. So there was definitely a discussion of how the new approach versus previous designs. Well, I guess one of the questions was yours, asking about, give me a number, 10%, 15%.
Yeah.
Right? And you didn't really get a firm response, but you did get an interesting response, which was, well, it's not always just about, it's important to look at those numbers, percent improvement, but also we're interested in looking at, Keller said, more fun ways to improve the product, right?
Yeah, I mean, Jim's answer was sort of, in some respects, very un-Intel-like, which was, it's not about committing to a particular growth rate. It's people get excited by big steps forward.
Right.
And so we want to excite people. That's actually kind of more of a Steve Jobs kind of mentality, which makes sense given that, Jim and Raja worked together at Apple prior to AMD.
Right.
So
I did think it was an interesting answer, though, because you were getting a complete non-answer right up until that point.
Yeah.
And for him to actually commit to something, even if it was sort of a sidestep, it was a valid sidestep. So I thought that was a good point of recognition. Actually, Intel in general seemed a lot more lucid this event, or self-aware this event than normally.
Oh yeah.
Where they there were I wrote down the quotes somewhere. We'll probably publish them, but quotes about there was definitely some humble pie and we're eating it. Right?
Yeah,
was one
I think
of them.
that was from Murthy.
Yes.
Murthy.
Yeah. And so Intel's self-aware, and they know their position in the market. They know they're challenged in some areas right now.
Yeah.
So that was very different to see from any company, but especially Intel.
Yeah, I mean, I think this happens with everyone, right? I thought that, AMD, when they were really on the ropes, was sort of similarly self-aware. And,
right.
But to me, going back to okay, what are the advantages that the 3D stacking and the 2.5D and all these more complex packaging schemes bring is that you can really optimize your silicon in different ways. And the easiest example, and maybe the most relevant, is the ideal process technology for a CPU and a GPU is really different. Right. For the CPU, we want the fastest transistors. We want the fastest circuit design. And that typically means larger transistors that are more loosely spaced. That means a tapered metal stack with more layers. And that's what allows you to run at greater than 5 gigahertz.
Which I'll mention also was a question we brought up of, okay, so can we expect at initial launch of a 10 nanometer desktop part which I specifically phrased it that way. So I didn't want to say, can you expect the same frequencies of a 10 nanometer part?
Yeah.
Because the answer is yes, at some point.
Right.
But the answer was still basically yes. So the question was, for the initial 10 nanometer product launches on desktop, will we see the same frequency as we see on 14 nanometer plus, however many pluses there are?
Yeah, I think it's. I mean, in some sense, 14 plus is a marketing thing,
Right.
but it's
Whatever.
The particular iteration of 14 nanometer that they're on.
And Raja more or less said, well, we're not going to release a product that's worse.
Right.
So that was the answer, I guess.
Yeah, I mean, I took his answer to mean two things. So one is, we're not going to go backwards in performance, and that probably means not going backwards in frequency. But at the same time, the first 10 nanometer parts are definitely not for the desktop, and so that's more of a mobile tune process.
Right.
So, when you're looking at these desktop parts, you don't care much about leakage, right?
Not nearly as much from.
Yeah. I mean, it's just not a super big deal, and you want to run at high frequency, and so then it turns out there's actually some like physical transistor effects that do let you run faster, but kind of hurt you on the leakage side. And so some of these things are typically perceived as being a negative, and from a process technology standpoint, at least a lot of people talk about them as a negative and something you want to minimize. But if you actually look at the real characteristics, it actually means the transistor runs faster, which for some people is more important than the other stuff.
Right?
Yeah, exactly. Right, but then when we talk about GPUs, right, we want maximum transistor density, and it doesn't have to run anywhere close to 5 gigahertz, right? You'd much rather have a more power efficient transistor that's only going to run at like 1 to 2 gigahertz. So that's one example. Another is if you're doing a mobile part, right, you might care a lot about low leakage.
Yes, I would say that is a particularly sensitive use case for it, yeah. Because you're dealing with, limited battery life, so.
Yeah, exactly. And even within the context of a microprocessor, there's still different blocks that want different things. A good example is your on-die memory, your SRAM. If you stick it in a processor, your typical processor is going to have something like 10 to 15 layers of metal wiring. Well, if you're just doing a raw die of SRAM, you don't need nearly that much. You can probably get away with 5. So you can cut down your cost quite considerably. So you could imagine a future microprocessor where you say, okay, the core and the register files and the L1 cache, that's all in cutting edge 10++. And then we're going to have a separate L2 cache and L3 cache that are in like 10 nanometer SRAM processes. Right, so there's a bunch of different ways to think about slicing this up, but until you have that 3D or 2.5D interconnect that is high bandwidth, low latency, and very power efficient, all those options are off the table.
Right.
So, from an engineering perspective, this just gives us a lot more toys to play with.
Right.
Not to mention the mixing the DRAM and storage and all sorts of other different things that are on different types of silicon.
Yes, there was a whole separate thing on Optane, for example, earlier today too, and all this stuff. So, what are your feelings overall with the 3D design approach that Intel is talking about? I mean, do you top level, you think it's the right direction, or challenges they might face that you think are significant?
Yeah, I mean, I think the biggest challenge is getting it done cost effectively, right? And we know that it can be done. Intel's done it with EMIB. TSMC has their approach that NVIDIA uses, and Google is using. But these are for typically machine learning chips and fairly bespoke things. We've seen a lot in recent HPC-oriented chips out of Japan from NEC and Fujitsu. And that's fine, but these are all chips that are being sold or valued at multiple thousands of dollars.
Right.
And I think the thing that gets interesting is, okay, can I deliver this in a $200 chip, $300 chip?
And with millions of units.
Yeah, exactly. And so scaling things into volume is always a little bit tricky, and so I'd say the cost side of the equation is that's the proof will be in the pudding.
Yeah.
And then there are some more specific technical difficulties. One of which is depending on how they're implementing things. EMIB is really interesting. And one of the things that's interesting is, unlike the TSMC approach, when you have your two die, they're really next to each other, and then there's sort of a bridge underneath, but it's a small bridge. And so one of the challenges is the two dies here have separate bumps to connect to the outside world and then to connect to the bridge. And those bridge bumps, the micro bumps, because they're different pitch, it actually makes things like structurally, physically, fairly challenging. Because you now have big bumps on one part of the die, small bumps on the other, and if they were to heat up and behave differently, you could get cracking or things like that. And so just the physical engineering around that and getting it to align correctly is not trivial. And TSMC's approach is a lot simpler. It's we're going to make everything out of silicon. It's all on one silicon piece in one module. So you've now have a lot more silicon, which costs you more money, but it is structurally a lot simpler. So, the question is, okay, how does this? So
does the cost of R&D and of validation and potentially RMA or at least wasted silicon or wasted parts, does that exceed the gains that TSMC would experience from doing it the easy way?
I would phrase it differently. It won't get into production unless all those things are under control. Right.
Of course.
And so that's why I say, the proof is in the pudding when they get to volume, and where do they introduce it? And it, I think a lot of these things, it's fine if it starts out in a premium part, and maybe it's really in mobile where you can justify paying for it. But the exciting thing is really to get that out everywhere. And then, also, I think, again, seeing the solutions that they have for power delivery and cooling are going to be pretty exciting.
Yes, definitely. Especially with Intel's renewed interest in better interfaces. Solder previously needs some work, but they're not anywhere close to talking about that today, I don't think, because it's you have to get through the rest of the product first. They're not even talking frequencies today.
I mean, it was very much a high-level type discussion. So, I mean, Intel seems to have this very interesting relationship with the high-end overclocking community, and that they absolutely want to support it. They put features in for it.
Right.
But then, on some of the parts, as I think you've talked about at length, their material choices leave a bit to be desired.
Yes,
it's hard to look at the cost equation. I don't really know how much this stuff costs in volume. So,
any other? So for Sunny Cove, I guess, is that the most immediate desktop part, or what's the most immediate thing we're looking for in the desktop space?
Well, most immediate. So okay,
because there were a lot of things today.
Yeah. So I mean, that was definitely one of the more exciting things, which was Sunny Cove is the code name for the CPU core that is inside of the Ice Lake family. Yeah, so I had always thought the core was called Ice Lake, but guess that's not true. So either they just made up the code name, or they kept it hidden. Who knows?
Didn't seem to exist online before today.
Yeah.
So if it was hidden, it was very well.
Yeah. And so they gave a lot more details on that, and it's a wider, higher performance core. That's pretty exciting. I mean, we've been sitting here with Skylake and its derivatives for a long time.
Yes.
So seeing those changes is great. And in part because Intel's had a lot of time to make these advances, and I'm sure it's very frustrating for a lot of the architects at Intel to have new architectures that they've wrapped up and have nailed down and can't ship.
Right. Tethered by their manufacturing process to some extent.
Yeah, and I mean, it's even worse for the folks who worked on Cannon Lake, which went from being a major product that was going to be across all the different segments to just
functionally dead. I mean,
Yeah, I mean they had a couple of products out.
There's the NUC, right? There's the i3 whatever,
but
8130.
then there was also the thing that was released before. But yeah, I mean, Canon is not really shipping in any real volumes,
right.
and it's more of
it's there for looks
Yeah.
at this point. Look, we did it. We shipped it.
Yeah. Well, but and that's the challenge, right? Which is, this was a design team, is let's get something for 10 nanometer up and ready as soon as possible so we can ship it, right? That's the TikTok way, and then wait for the architecture. But if the process isn't ready, then when you have your new architecture, it's going to be better than the old one. So
right. And I will note as well, they Keller and Raja Koduri, which I haven't properly introduced either of them. Yeah. But if you don't know, Raja Koduri, I did a video with him a few years ago. He used to work at AMD at RTG, functionally was the lead, and now at Intel.
Yeah.
And Keller, known for also doing significant work at AMD recently.
Yeah. So, I mean, Jim's career is I mean, both of them have had pretty lengthy careers.
Right.
Like Jim was at Digital initially, then he went over to AMD.
They were both at Apple for a little bit, I think?
Yes, they were at Apple together. Jim was also, I think he was at SciByte, and then he left AMD. He was at PA Semi, which was doing PowerPC chips for Apple, actually, for their notebooks. But then Apple famously switched to Intel, and that was kind of tough for PA Semi, but Apple eventually bought them, and so then that for the basis of the now the CPU and implementation team.
One of the things he was talking about was continuing to potentially use 14 nanometer plus or whatever, and not just phasing out these processes, right? Because if it's still an adequate piece of silicon for what you're trying to achieve, I guess, then why complicate it with something more expensive and with more limited fab space?
Yeah, and I mean, I think his point was a new process is no longer everything to everyone. And so, and I think actually we've seen this for a while, right? With Broadwell.
Right.
Broadwell was mostly interesting on the mobile side, and the desktops, particularly in the enthusiast side, were just not there.
Right.
There were certainly some, I think, like 45 watt desktops, but I don't think there was really a 90 watt client socket Broadwell. And that's fine, but the point is, okay, so if we get a process that's good for mobile and we lead with that, then we're going to continue shipping the old process for desktop stuff.
Right.
And the other thing is...
And he did mention a potential 15% increase in frequency or performance or something like that. Did you catch that?
Well, yes. Yes. So he said that they had come up with different ways to tweak the transistors to boost frequency.
Right. It's just a question of whether they have a product to do it on, I guess, at this point.
Yeah, and what is the particular tweak? What's the cost? And
right.
But I think the point is there's a lot more performance you can wring out of a process through incremental tuning, number one. And then the other thing that's kind of interesting, you can do a mix and match with 3D or 2.5D. So if you have, it just gives you a bit more flexibility. They say you could say, okay, look, we want to take a 14++ CPU and combine it with a 10 nanometer GPU, or whatever. So. Yeah, and I think that was his statement of, we're going to have several process technologies in high volume that we use across our product line simultaneously, and it's just one more variable that we get to choose from.
Right. Any final points you want to add in here? Anything really major we didn't talk about that you think is worth mentioning?
Well, I mean, one of the other things I thought was interesting is they did talk about on-package memory.
Yes. Yeah.
Right, and a lot of this was in the context of the integrated GPU. But they also talked about in the future discrete GPUs, and so I think it's great to see people looking at, okay, how can we boost performance?
And before anyone gets too excited, the way in which they talked about discrete GPUs in the future primarily pertains to not talking about them today.
Yes.
So
yes.
don't get too excited.
Yeah.
But
yeah.
it was mentioned, yes.
Yeah, right. So I think that it's, as many things at Intel, it's a gradual process, right?
Mm-hmm.
So I think the first step is a higher performance integrated GPU, and then, next couple of years we'll start seeing more variance at higher performance levels, and my guess is the first thing they do will not be a 300 watt monster.
Right.
It'll be more like a mid-range part, and that's fine. But I think the point is, okay, because they're looking in that direction, they're now driven to find some in-package memory solutions. Talked about using LPDDR4X, maybe LPDDR5 in the future. But that could be quite interesting if it's architected the right way for CPU performance as well. I mean, one of the sort of interesting hoary old tales of the industry was I think Crystalwell, the Broadwell with 128 megabytes of EDRAM in package.
Yeah.
It turns out that 128 megabytes of L4 cache was worth something like 800 megahertz on some workloads.
Okay, yeah.
And so that actually beat, at intro, some of the high frequency Skylakes on some games.
Right, yes, I recall that, yeah.
Yeah.
It was also a very rare part, too.
Yeah, I remember, so I got one to test, and Anand was so annoyed at me because I tested it, and I have some internal numbers that I used for some of my own, calibrating some of my own models, but I never published anything. He's like, there's 3 people in the world who got to play around with that. You sat on yours for like a couple months and didn't publish. And I'm like, yeah, well, what are you going to do?
Yeah.
But the thing that's interesting is once you start playing around with this embedded memory, even if it's for a mid-range GPU, it'll inevitably get pushed in different directions, right? And so maybe we will see an option to get a high-end, 5.5 gigahertz,
Right.
Ice Lake with embedded memory. That would be really cool, And they were talking about. I think the slide said something along the lines of a gigabyte. That's a lot of memory.
Yes, it is significant.
Yeah, right? I mean, I don't know, how big are some of the levels in these games? If you could keep the whole thing in cache, that'd be pretty awesome.
Yeah, gigabyte is, especially because, the biggest things you're going to be dealing with are things like textures.
Yeah.
And even though they're large, but a gigabyte is significant when you're talking about typically 128 megabytes in the biggest recent scenario.
Yeah.
With Crystalwell, I guess that was, or whatever it was called. Yeah. So I don't know. Other than that, I think that's a pretty good.
Yeah,
recap.
They covered a lot of stuff. I mean, there's plenty of other things we could talk about.
Yes.
FPGAs and AI and machine
Optane
learning
and everything.
Yeah. On the Optane side, I think we both agreed. We were chatting about this a little bit earlier, but it's really exciting. Mostly in the DIMM form factor.
Yes, the DIMM form factor for sure, and I would estimate that the majority of our audience is familiar with Optane from its initial implementation, which was M.2 as a cache drive, and that was a terrible start to Optane as a technology.
Yeah.
And unfortunately, because the name is the same as in the DIMMs, everybody is just associating it with that and going, Optane is garbage, based on the comments I've read. So, just to point out, the DIMM stuff's pretty cool.
Yeah.
But, the cache drive is kind of a different story.
Yeah, I think this was sort of a scenario where basically Intel needed to go to market with a product, and the DIMMs weren't ready because the server processor it was going to attach to wasn't ready. So, that's going to be Cascade Lake, which Sailesh talked about for a bit today. And I guess the one interesting thing is, of course, Cascade Lake is a server chip, but as we all know, the server chips do show up as the, are they calling them Core i9s now? It's hard to keep track of what
more
the
or less,
guys do.
but yeah.
But the really high end are based on server chips. So, we may get in the not too distant future, like Q1 of next year, enthusiast systems where you can get Optane DIMMs in pretty large capacity. So
Right.
that would be super exciting, and I bet they would be monsters to benchmark.
Yeah, it would be it would be very different because
Yeah.
you're testing responsiveness at that point too, right? Not just
Oh yeah.
it's the whole system would in theory be much faster.
Yeah, and I mean, I think, this is just something I was thinking about sort of casually as kind of a wild and crazy idea. But, I think on my system, I'm currently running with something like maybe a 300 or 400 gigabyte SSD for all my applications in OS. And, I have a bunch of hard drives for holding media and other things. But, you can get a terabyte of Optane DIMMs, no problem. So you could actually just have a PC where everything sits in Optane.
Yeah.
And, if the latencies are call it 300 nanoseconds for everything,
Yeah.
that's a lot better than the microseconds we're used to for an SSD.
Yes,
So
definitely.
Yeah, I guess, that.
Shove it all into memory constantly.
Yeah, and it's
basically,
permanently in memory, right? So, how fast is Windows booting then?
Right. Yeah, at that point you just become bound by things like the post check.
Yeah.
Right? Just stuff like that, yeah. So really cool stuff on the Optane side we won't dive into.
Yeah, we
but-
can always talk about it later.
Yeah. And for more of David Kanter's work, Real World Tech, I guess, is officially where
Yeah.
you can find some of his writing.
Yeah, I'm on Twitter, of course. The
Kanter,
yeah.
And then MLPerf, you've had
Yeah.
contributions to as well.
Yeah, and mlperf.org is where you can go to check that out. And, actually today is kind of a big day for MLPerf. And for those who don't know, it's an industry standard benchmark for machine learning, and it was started out by folks from Google, Baidu, Berkeley, Harvard, and it's now really grown into a great organization. And so we're going to be having some results from the first round of machine learning training benchmarks. And if you've listened to NVIDIA or Intel or Google or frankly anyone else,
Basically anyone, yeah.
Yeah, that's like a big topic. And I think actually, when we were talking about some of NVIDIA's RTX, some of the ray tracing, actually uses machine learning
Yes.
to smooth out the results. And then there's also been some work from NVIDIA on using machine learning for anti-aliasing. So, while it's traditionally sort of a more data center workload, the results are absolutely relevant to consumers everywhere. And it's something that I've been working on a lot and I'm pretty excited about.
Yeah, and I guess I'll go ahead and put a link below if there's a relevant site or something I can link to.
Yeah, mlperf.org. And depending on the time of day, there may be results up there for the first round, which is pretty exciting.
Very cool. So check that out. Well, that's it for this one. So as always, subscribe for more. You have I'll give you links below for Real World Tech. And you can also go to patreon.com/gamersnexus, help out directly, or the store. And David, thank you for joining me.
Absolutely. Good to see you again.
Good to see you. We'll see you all next time.